And now, welcome Professor Trajkovic, our guest from Canada, but I know that currently you are in Prague, in Czech. Welcome on our IEEE Day. This is Professor Trajkovic, who is IEEE Distinguished Lecturer and will present machine learning for detecting internet traffic anomalies. So, floor is yours.
Thank you very much, Professor Gjiljak, for inviting me. I am in Prague, so I'm close by. And I understand you're giving me 1 hour for the talk?
Yes, exactly.
Thank you, and I'm glad I connected. So congratulations on celebrating IEEE Day in Poland. And this is my second time that I'm presenting. And I try to make it a little bit different from last time, just in case you attended my talk a year ago. I'm going to share the screen. Let's see, this one.
Oh, yes, we see your screen.
And I think we should start from here.
Yes.
And I think I should do it properly. So today I'm going to talk about machine learning for detecting internet anomalies. Last time I talked about machine learning for analysis of network traffic in general. So I provided some history and some introduction, but you really don't have to remember my talk from last time because I'm specifically talking today about detecting internet traffic anomalies. And so I come from Communication Networks Laboratory. I'm in School of Engineering Science at Simon Fraser University. We are located in Burnaby, but nobody knows where Burnaby is, so we usually say that we are in Vancouver, in British Columbia and Canada. So let's do that properly. So this is the outline of my talk. And so I would like to introduce the topic. Why is it important to detect network anomalies? And you probably realize it's important because it's affecting our work, our studies. And unfortunately, these kind of anomalies are happening as we speak, and they're evolving and they're changing. So for example, worms and viruses, they were predominant 2 decades ago, are now replaced with stuff like ransomware attacks. And sometimes the anomalies do not come from bad intentions. Sometimes they happen because the system fails, there are electrical failures, there are misconfigurations of routers that are not intentional, but sometimes engineers make mistakes. So some of these anomalies are not always malicious. It's very important to have data for this kind of analysis. So data collection is very difficult, very expensive, and it's not very easily available. So if you want to collect data from deployed networks, that means real customers, it's very difficult to get permission, and the equipment is rather expensive. But research community usually relies on data that are readily available to the research community, and I'm going to talk about 2 repositories. They have been collect data from internet over the last 2 decades, and I'm going to mention them, and the data is available to research community. Of course, one has to do the work in order to clean the data, to curate the data, to prepare the data for analysis, but it's available to research community. So you don't have to have your own connections with providers. You don't have to buy your own equipment. If you are interested in this kind of analysis, the data from deployed internet is available to the community. One thing that I thought is very important, especially today, when we have these ready Python packages to do various machine learning algorithms and evaluate various performance for various tasks, it's very important to remember that feature selections are very important. So we have our data. I'm going to talk about feature selection. In the past, the feature selection algorithms were separate from machine learning algorithms in a way, so you could see what kind of features were selected. Combinations of features are also very important, but somehow that's all now hidden with these ready Python packages. So I usually tell my students, could you tell me which features were important? Which collection of features is important? How do you combine the features? So I'm going to talk about that a little bit because we improved some of the algorithms by specifically keeping in mind that we have to worry about feature selection. And then I'm going to talk about various machine learning models. Of course, very popular variety of deep learning network models, and I'm going to mention them all. We also introduced, and I think I probably talked about that earlier, about broad learning system. That's the departure from deep learning. One doesn't have to go deep inside the network, thousands of layers. One can actually go broad. So 2 or 3 years ago, there was a proposal to use a BLS system, and it turns out that it has some very nice features. In general, these have comparable performance to deep learning, but they have one advantage: they are very fast. And so in this kind of work, it's important to have fast algorithms, because if there is something bad happening in the network, you would like to identify the onset of the attack, the onset of the anomaly, so that system administrators can take that into account and take down the system, the equipment, the router that has been attacked. So the speed of the training of the model is very important, and broad learning system has one advantage, and I'll talk about that at length, that they are very fast. At the same time, when broad learning system was introduced, but Philip Chen and his group, at that time he was at Macau University, currently he's in South China Institute of Technology. At the same time, people were proposing gradient boosting decision trees, and we experimented with them also. It turns out that they have a good performance, and they're also very fast. I'm also going to describe what kind of experiments we do, and of course, performance evaluation, because one would like to know what kind of performance in terms of F-score, in terms of other parameters that we use, how do these algorithms perform? And then I'll conclude. And for people who are interested, I usually put references with the most relevant sources of information, just in case you are interested in the field, you might want to read some of the well-known references that we also used. So introduction, measurement of traffic has been around for a long time. But in the old days, that measurement by telephone companies. And usually those measurements were used for their own algorithms, for doing the prediction, for deploying the elements. Nowadays, when we use networks not only for telephone calls, but also for internet, right? For data, for images, for videos, the traffic has changed. But the traffic measurements were always used in order to help understand the characteristic of network traffic. They are really basis for developing traffic models. And I'm talking about the collection from real deployed networks, right? Not artificial, not simulations, not testbeds. And they're also used to evaluate performance of various protocols and applications. So if somebody is interested to introduce a new protocol, which is difficult these days in the internet because it's a legacy system, but applications, there are many, and they're popping up every day. So if one would like to evaluate the performance application, one would like to use realistic traffic model. And how do you create realistic traffic models? By studying the traffic collected from deployed networks and trying to create the models. Traffic analysis is very important. It provides information about how is the network used, and the service providers would like to know that. And it really helps understand the behavior of the users. Users don't behave the same over the 24 hours of a day. They don't behave the same over 7 days of the week. And also, there is this notion that the traffic has this seasonal effect. It really depends. So one would expect that, for example, over weekends, network is used differently, and traffic data shows that. In the morning, in the afternoon, it really also depends on the network. I might not talk about it, but for example, when we studied the network used by police, it turns out that the network is very used around 11 p.m., midnight, because most of the crime happens at that time, right? And so that's important to know. Where do you want to service your network? You don't want to service your network at the time when it's heavily used. And of course, internet is used differently. Traffic prediction is difficult, but it's important to assess future network capacity requirements, right? And the providers have to plan for future network developments. So all of this was there for many, many years in the past, but it's becoming even more important now when network is so heavily used because we use internet every day, and even my talk would not be possible if there was no internet to carry the data that are generated by my talk. So data collected from network users are used to evaluate network performance, to characterize and model network traffic, and very interesting, to identify trends in the evolution of internet topology. Because you probably realize that over the last 3 or 4 decades that we use internet, the topology of the internet has changed. So for a while, maybe a decade ago, we were studying the traffic in order to understand how the internet topology has changed. And we also, more recently, and that's the topic of my talk, we would like to classify traffic and network anomalies. So that's why the data is so important. And I'm talking about good quality data. And for this talk, I'm mainly going to talk about supervised machine learning, so the data has to be labeled. And you probably realize that labeling the data is very time-consuming task. And probably the future of machine learning is really unsupervised machine learning, but that's the future. So this is something about the characteristic of traffic, because we have to understand the network, but we also have to understand the traffic. So this is an example of a pictorial view. Why do we consider that traffic that we see today that's carried by internet is what we call self-similar or fractal, right? So this is, for example, a genuine impact trace, real trace, and you can see 3 graphs. On the left is one scale, time scale, when each point actually captures how many bytes there are in the four frames of this movie. And since this was coded with 40 milliseconds per second, 40 milliseconds frames, 4 frames is equivalent to 160 milliseconds. So for every 160 milliseconds, I'm going to count how many bits are there, and I'm going to plot it on the graph. And you can see peaks and valleys, right? So we can see that it's very bursty traffic. There are many peaks and valleys. So that's one time scale. In this case, what's 4 frames? Let me zoom out. Let me say, okay, how many bits are there in 16 frames? That means my time scale is 640 milliseconds. So of course, the vertical scale is going to change, because every point now represents the number of bits in 640 milliseconds. But one can see that qualitatively, the graph has not changed. Qualitatively speaking, I still see the peaks and valleys. Let's do this once again and change the time scale to 64 frames. So I'm collecting the number of bits that appeared in 64 frames over 2,506 milliseconds. Again, peaks and valleys. Of course, the vertical scale has further increased. We are talking about 5 million bits. But when you look at this, you would say, wow, no matter what time scale I have, I qualitatively see the same pattern. And this is why we say the traffic we see today in the internet, it's what we call self-similar. So that's something about the traffic. And I'm quoting both the result and also this way of representation to Walter Willinger and his group, his team, who published a seminal paper, IEEE ACM Transactions of Networking, in 1994. And in 1995, they got a Bennett Award. That's the highest award for the best paper in all IEEE transactions, which is really indicating how important that finding was. Because before this, people always thought that it's good enough to model traffic using Poisson processes. And that was nice. It captured qualitatively the phone calls. And telephone companies were using Poisson processes in order to create their models. And it was very tractable. You could apply queuing theory. You have closed form solutions. But unfortunately, the traffic that we see in the internet that carries voice and video and images and data, it's far from being able to be modeled using Poisson process. And so that's about the traffic. Next thing is about the topology. So this is a view of internet that was collected from CAIDA, and I'll mention the reference later, because a decade later, or less than that, Brother Falutzos, these are 3 brothers actually, and their collaborator, published a paper where they studied the internet topology. And they said, well, in the old days, many systems could be modeled with random networks, random graphs. And that was good enough for many engineering systems. And for many years, we use randoms in order to capture the connectivity and topology engineering systems and some other phenomena in nature. But it turns out, when you look at the real data, and this is real data that captures 500,000 nodes and over 600,000 links that is represented in this graph, we can see that this is not random. This is not completely connected graph. This is not a random graph. So they came up with this proposal that the internet is actually something what we call scale-free graph. Scale is related to the degree of the node. That means there are nodes that are very connected, that are nodes that are isolated, and as the internet grows, and probably it grows as we speak, you can see that the nodes that are very connected are even going to get more connected. So it's this idea of rich gets richer, right? But that also indicates that if we want to model the internet, we should try to qualitatively capture the connectivity. So you have actually, there are algorithms that are going to let you create a topology that captures some of these notions of scale-free. Okay, so that's about the traffic and the graphs that are used usually to simulate the networks if you want to evaluate performance of your algorithms. Now about the data collection, right? So we collected data from Internet Border Gateway Protocol. This is BGP. It's a de facto standard for routing. Anything that goes through the internet goes through BGP, right? I'm not saying it's de jure, which means somebody forced it, but de facto everybody is using it. And so we are collecting this BGP data, and we are going to look at BGP anomalies. And as I mentioned, 2 decades ago, computer worms and viruses would take the internet down. Slama in 2003, Nimda in 2001, and Code Red 1 in 2001, around June, took internet down for a prolonged period of time. So NewYorkTimes.com was down, Yahoo.com was down. So you can imagine the impact on the economy where you have a site that's more than 24 hours down. Well, the evil people on the internet may actually do this at that time, but the system administrators become smarter. So the viruses and worms that work in the past would not work today. And sometimes electrical failures that are not intentional also took internet connectivity down. And we looked at the data from a Moscow blackout because there was a trafo station. It was called Chigano trafo station south of Moscow failed, electrical failure. And one can see in the connection of internet traffic, right, the connectivity was lost. More recently, there was a Pakistan power outage in 2021, and we also looked at that. What's very, unfortunately, very popular now are ransomware attacks. And they're very different from worms and viruses or electrical failures. And you probably know what the ransomware is. That means somebody encrypts the data. And if I want my data back, I have to pay. And many institutions, universities, hospitals, private companies, they're actually the target of these attacks. And sometimes you hear a bit about this on the news, right? And so we looked in more recent attacks. In 2017 was WannaCrypt, and some people call it WannaCry. And into 2021, last year, a company called Vestro was also attacked. And they have to pay. But the phenomenon is a little bit different. And what I'm going to show that we probably need better algorithms in order to have a better performance when we apply detection to ransomware attacks. And there are sometimes internet protocol prefix hijacks, sometimes misconfigurations that are really not malicious, it's just a mistake in programming the router. 2 collection sites that I mentioned are called RIPE and RouteViews. RIPE is Resolve IP European. The collection sites are in Europe. There are many. RouteViews is a project from University of Oregon, and most of the collection sites are in North America. But keep in mind, they all collect data from the same network that we call internet. A little bit about historical view of these internet forms. So giving you information about two collection sites, RIPE in Europe, outages in North America. They have been collecting data over the last 2 decades. These are the data sets. Outages didn't collect early enough, so we do not have a data for Code Red 1 and Indra from 2001, but they do have a data from 2003. So you can see SLAMA right in both sides. We are indicating what is the duration of the regular data, what's the duration of the anomaly. We, of course, divide the data set into training and test. And these are the gory details about where was it reported that the anomaly started. How do we know that? From reports, from email messages, from white papers, right, from published literature. So these are the start and end dates of these worms as accepted, as reported. Power blackouts and outages, we also looked at those. This is a Moscow blackout, this is Pakistan power outage. Both collection sites, we sometimes compare, does it really matter where we actually take the data? Of course, it's always better to take a data close to the epicenter of the event. So for example, for Moscow blackout, it was better to gather the data from right because the collection sites are in Europe. So these are gory details about, just to sort of give you a hint that you have to be very precise when you work with data. This is about ransomware attacks. Because when I was presenting this kind of work, people were always saying, oh, this happened 2 decades ago, how relevant it is now. So we decided we are going to become more up to date. So we are looking now at ransomware attacks. This is WannaCrypt, Vestrock, regular and anomaly in terms of minutes, separation into training and test. And for our data, we used 60% of the anomalous data for testing and for training and 40% for test. Usually engineering approaches to say 80-20. 80% of the data used for training, 20 for test. But in our case, for the data that we deal with, 60-40 was better. And this is a start and end time. It's not really very easy to figure out when is the start and end time of the anomaly. So you have to read the newspapers, you have to read white papers, you have to read the reports, but more or less, that's what we consider. That, for example, WannaCrypt started on 10th of May at midnight and ended on 17th of May. You can see the duration is 7 days. And for Vestrock ransomware, from 21st of January to 31st of January. So that's about the data, right? So we usually like to look at this from a pictorial point of view. So this is a SLAMA that happened in 2003. We are looking at some of the features for border gateway protocol. And specifically, we are looking at the number of BGP announcements. It's one of the features. That means the routers are announcing which are the good paths. And we are also looking at the number of announced network layer reachability information prefixes. So these are 2 features. There are many features in BGP. We actually looked at 37 features. But we took these 2 just to show you how it looks when you look at the right collection site, routers collection site. We talk about SLAM in both cases, and these are 2 features that we were looking at. And one can see that during the time of the anomaly, you can see very different behavior. And usually, the worms and viruses are represented by increased in the volume. So you can see increased in the volume, right? Just disregard the spikes. They probably happen something happened in the network. But you can see during the worm attack, you can see the increased volume, the increased number of BGP announcements. And the same was for increased number of these NLRI prefixes. But it's good to look at the graph and just sort of to see the data in general. This is the Moscow blackout. It was more difficult to identify. It lasted only 4 hours. And so this is May 25th. You can see the increased activity. And at that time, this is already 2 decades or 15 years ago, there were not many other anomalies happening. So it was easier to identify the anomalies. So you can actually see that there are a lot of things happening here during these 4 hours. I think it was after midnight. I mean, we actually had to read newspapers in order to figure it out. But one can see that the volume feature is one of the features that indicate that something is happening, something abnormal is happening in the network. This is, sometimes we do these three-dimensional views. This is the number of announced prefixes. This is number of implicit withdrawals. One can see that during the time, red means anomaly. We label it as class 1. Blue means regular points, right? And we look at the times before and times after, and then times of the number. So that's how it looks like, both for right and for out use. We always compare these two. As I mentioned, the data is collected from the same network, just the collection sites are from different locations. Ransomware is more difficult to identify. First, it's very difficult to identify when it starts and when it ends. So this is, for example, WannaCrypt that happened in 2017. We are again looking at two features of BGP, announcements and announced prefixes. And this period of time is when the ransomware took place. We always take days before as a regular traffic, days after as a regular traffic. And during this window, when ransomware was reported, we are going to have a very simplistic approach. We are going to assume that everything within the window is anomalous. And you might immediately say, well, that's not really fair, because during that time, there were also regular transactions, regular packets that were not anomalous. So later on, we are going to try to refine our approach a little bit. But at the beginning, a course assumption is everything before May 12th of 2017, everything before is regular. Everything after May 16, actually it's May 17 because of the midnight, is going to be a regular. Everything inside is anomalous. And later we're going to refine that. But for now, we're going to assume if that ransomware was reported at that time, everything inside is anomalous. And we are going to try to figure out how to classify a point that's given. So classification means, can the algorithm figure out whether the point is regular or it's anomalous? And so that's the goal. So we have two-way classification. Point is anomalous or regular. And of course, one can make the life more interesting and say, well, what kind of anomalies do we have? We don't have to have a two-way classification. That's more difficult. One can say, okay, if I have 3 viruses, Slama, Nimda, and Codred1, can you tell me which virus that is? And we worked a little bit on that, and of course, that's more difficult. So we're going to have a simple approach of having a two-way classification. If I have a data point, I would like the algorithm to figure out whether data point is anomalous or regular. So that's the goal. Okay? So that's how it looks like. This is Vestrock. When we started this work, it just happened. It happened in January of 2021. It attacked a big company and actually took a lot of operations of the company down. And this is a reported period of ransomware, right? Everything blue is regular. Everything red inside is anomaly. And as always, we have two views, right and right views. Vestrock is a company in North America, and probably the data from route views is a little bit more reliable. So that's about data collection. Features, very important. So in the old days, we use various feature selection algorithms to select most relevant features and also to combine them. Because, of course, one is going to spend less time if you select the relevant features. You don't have to spend too much time to train and test your data. But it's important to select relevant features. Not all features are relevant. In addition to that, it's important to combine the features that are going to actually show the clustering in such a way that the algorithm works better. So in the old days, there were various feature selection algorithms. Why are they used? To reduce redundancy. Because if you use redundancy, your algorithm can do the training fast and the testing fast. So Fisher, for example, algorithm was used, MR in the past, mutual information base, odds ratio. But we reported this a long time ago. Now we were very interested to find out how decision tree is going to do in terms of feature selection. And we also used extremely randomized trees. We call them extra trees, and I'm going to show you some results. So this is a little bit about extra trees. It's more of a novel algorithm. We are looking at the gene importance. to compute feature scores in a given data set. So this is the expression for calculating this Gini importance, and these are all the gory details about. And sometimes these functions are already built in, so you don't have to program it. So, but this is how we use the Gini importance to compute the scores. And based on the feature scores, of course, we are going to take the features that have a higher score. Dimension reduction, very important. And we are going to use unsupervised learning to do dimension reduction. So this is, sometimes we call it semi-supervised because some of the algorithms are supervised. So machine learning algorithms are going to supervise, but the dimension reduction is going to be done using unsupervised learning. So we are going to use unlabeled input data to train the model. We are going to transform original data into low-dimensional data, but we would like to preserve the characteristics of the original data. We are going to use autoencoders as unsupervised neural network to learn representation from a given data set. And deep autoencoder with various long short-term memory and gated recurrent unit hidden layers were used for dimension reduction. Because in some of these data sets, you have the dimension is 80 features, 85 features, 90 features. So if you want to use all of them, it's not necessarily true that your algorithms are going to have better performance. And there is always a trade-off. How much time and CPU do you want to use? Do you really have to use all 80 features? And it turns out that dimension reduction is very important. So this is how autoencoder looks like. This is a high-level training process, so that there is encoder, there is a classification algorithm inside, code, and there is output. So for example, what you see on the right-hand side, this is input data, this is encoder, this is the middle part, classification algorithm, decoder, and I would like now to compare the left and the right, because the left is a full system, full dimension. The right is a reduced dimension. And you can see that actually when you do this, you can preserve the characteristics. And so you can see, I think this is probably slammer. You can see this period when the worm attacked, and you can see it here, right? You can also look at the other features. And in this case is, I think it's minimum AS path length. It's one of the features. It's not a volume features. We call it AS path features. And you can see the pattern is preserved. And for the other algorithms, sometimes you can see it doesn't really capture everything. But the importance is that we reconstructed the input data from lower dimension. So in case of BGP dataset for slammer, sometimes we do this kind of graphs to show you clustering. So for example, this is number of BGP withdrawals, average AS path length, number of BGP announcements. These are three features of the BGP data. And one can see that there is a separation between blue and red. Red is anomaly, blue is regular. We call it class 1 is anomaly, class 0 is regular, and one can see the separation, both for ripe data and for slammer data. If you look at the Moscow blackout, the separation is not that visible. So one might suspect that machine algorithms are not going to do as well, because if you do not have a good separation of the classes, it's very difficult to do classification, because this detection of anomaly is really a classification problem. So one can see here, maybe I can see blue and red, but it's all over the place here. And this is for Pakistani power outage, because I'm really talking about three different anomalies: worms and viruses, power outages, and the ransomware. So this is really not that separable, blue and red, okay? And so in case of ransomware, it's even more difficult. One can see that this red and blue overlaps, and this is a three-dimensional figure. We actually selected very carefully the features that we are going to plot. We rotated the 3D graphs, so that's the best view, but it tells you the separation into two classes: regular and anomaly, blue and red, 0 and 1 is not that easy. So this is Vanacrypt, this is Vestrock, and you will see, based on the performance of algorithms, that the algorithms don't do that well when we deal with ransomware attacks. And the mechanism is very different. So we probably have to do more work in order to select better algorithms. So now about machine learning. deep learning is very popular, right? People already proposed a number of intrusion detection systems. They employ diverse algorithms, deep learning, CNN for convolutional neural network, recurrent neural networks, so RNNs, deep belief networks, and autoencoders. We didn't work very much with deep belief networks, but with autoencoders we did, and we used autoencoders for dimension reduction. And everything else is supervised except autoencoders. We also look at the boosting algorithms, AdaBoost, and also GBDT. It stands for Gradient Boosting Exchanger Tree. And as I mentioned at the beginning, we find them very promising because they are very fast and have comparable performance. So in terms of supervised machine learning algorithms, we have been working on this for over a decade. We started with support vector machines, very robust, but rather slow. We work with convolutional neural networks. We work with recurrent neural networks. Two families, LSTM, long short-term memory, and bidirectional LSTM. And we also worked on gated recurrent unit, or GRU, and bidirectional GRU. Broad learning system, sort of novel approach. It was introduced in December 2017 at the Little Conference in Shenzhen, and later on, we got quite a few journal publications, and we also contributed to improving the algorithm by introducing feature selection, and I'll mention that. That was the major work of my Ph.D. A student who in the meantime graduated. We experimented with a variety of GBDT algorithms, XGBoost, LightGBM, and CANBoost. So this is how convolutional neural networks looks like. It's a very high view. So we have an input layer. We don't work with images. Our data are time series data. So when we have this collection, it's a time series. So if the algorithm is suitable for images, we would flatten the image and we will make it as input layer as a series data, as you can see on the left. Then we have convolutions, we have feature maps, max polling, convolutions, feature maps, max polling, flattening, and finally, we come to the fully connected layer and output layer. And I want to mention that even though we do have a GPU, many of these algorithms we find would work very fine with CPUs. Right? So, of course, GPU is going to be probably order of magnitude faster, but not all algorithms that are code that's readily available is suitable for GPU. Now, this is a deep learning network. It's really not very deep. We talk about 37 recurrent neural networks, 80 fully connected layers here, 32 and 16 fully connected layer hidden nodes, and finally the output. So we are not working with thousands of layers because the performance is good enough, and we also are concerned about the time that's taken in order to train and test the model. And you have probably seen the LSTM. This is one of the latest papers. It was published in 2017, even though the algorithm was published a long time ago. So this is a repeated module. This is the LSTM cell. You can see it has a lot of elements inside. It has a very nice mathematical representation, which I made in hidden slides, but there is a math behind. So control theory people are very interested to find out why these algorithms converge. What is the time convergence, right? And so it's a still open problem. So I want to say that there is a math behind, it's just not trial and error. GRU is a simplified version, still good enough, but of course the training and test time are shorter, and also the requirements, the calculation, the CPU requirements are shorter. It's a simplified version of LSTM. Broad learning system, different approach. Instead of going deep, now we can go broad. And that's why it's called broad learning system. And as I mentioned, it was introduced by Philip Chen and his students. And the first journal publication was in January of 2018, but they already introduced the algorithm in 2017. So this broad learning system has very interesting feature that it can be incremental. That means if I'm not happy with the performance, I can increase the number of these nodes and the number of these nodes. Not only that, I can also increase the input. So I can add a new input, and that makes it incremental. So these are map features. There are two different kinds of nodes: map features, enhancement nodes. So there is input and there is output. So it's broad. There is no depth in this algorithm. If I'm not happy with performance, I can increase the number of map features without retraining the network, because these weights are dynamically calculated. I can increase the number of enhancement nodes, and not only that, I can add new input. So if we have a huge data set, it's very suitable. You train and test with a smaller data set, and then you can add additional data. So there is a math theory behind. This is the original BLS. There are flavors of BLS, right? And just to tell you, there is a formal mathematical representation. Something here which is important: the algorithm is fast because it doesn't use backpropagation. They use Moore-Penrose pseudo-inverse, and that makes it very fast. Okay, so we can actually calculate it using ridge regression and also the theory behind, right? And so it's modified in order to include additional map features, additional enhancement nodes, additional input nodes, and that makes the algorithm what we say incremental. Okay, there are flavors. This is, for example, radial basis function, a BLS extension. The radial basis function is implemented using Gaussian kernel, right? One can add a depth. So if you're not happy with the flat feature, you can add cascades. So this is a view when I'm cascading map features. So this is the depth. So we're adding the depth if needed using cascades. And for some image processing, and the algorithm was first introduced really for images, they did quite a few cascades. We didn't need more than 10 or 20. But in case of image analysis, I recall that Philip Chen has reported like thousands of cascades. We didn't need it. And one can actually do enhancement nodes. You can do incremental, you can do new input, and you can add some depth. And in this case, we call this depth cascades. Something that we contributed, so it was to add the features. So this is a variable feature broad learning system. One can see addition. And so that was our contribution to improving the algorithm. So you can see the same structure in the top, and we have this feature selection algorithm. And so this feature selection algorithm is an addition, right? So you can select the features and then use the BLS. And we published it in a JSAT, that's a Journal on Selected Areas in Communications last year, okay? And so we also can do this for incremental learning, right? For map features, enhancement nodes, and here is our contribution with feature selection algorithms. So that was the heart of the matter for the PhD thesis of my student, okay? And this is with cascades, so you can see these are the cascades. These are depths, similar idea. So the main idea is to add feature selection before you start doing BLS. And of course, incremental learning. So the students spend a lot of time drawing these beautiful graphs that then I can use. Gradient boosting decision tree was introduced approximately at the same time as BLS, but it turns out that it's equally good. It's equally fast and comparable performance, okay? So this is the idea behind GBM. These are gradient boosting machines. So these are boosting algorithms. They use gradient descent to minimize the loss function. So it's really optimization problem. And GBDT stands for gradient boosting decision tree. It's a variant of gradient boosting machine, and it uses decision tree as an estimate. So this is how the gradient boosting model is generated. We look at the error. As the iterations increase, hopefully the error is decreasing. It's an optimization problem. So these are gory details about GBDT. This is all publicly domain, so you can actually look at the mathematical background behind. So I'm going to skip this a little bit, okay? It's really the GBDT is the optimization problem. You want to minimize this objective function, right? It's called the loss function. 3 variants of GBDT: XGBoost for extreme gradient boosting, light GBM, which is very interesting to us, and the name light says it's fast. It's a light gradient boosting machine, and then categorical boosting, because if your features are not numerical but categorical, For the other algorithms, you have to convert them into numerical features, and there are algorithms to do conversion. But CAD-Boost can deal with categorical features directly. So these are some gory details about XGBoost in terms of how they operate. LGBN has this acceleration, and the training speed is reduced by using gradient-based one-side sampling and some other exclusive feature bundling, right? And as I mentioned, CAD-Boost has a big advantage of dealing with categorical boost. And let me talk about experiments. I think recently we generated the software. I think we are waiting for publication that was just accepted in order to put it on the GitHub. This is architecture. We call it a BGP guard, right? So this is a core. We have all the process like data download, BGP update messages from both write and routers. We need tools in order to extract the data. So Zebra dump parser is already available on these collection sites. We do feature extraction. We created our own tool. At that time, we wrote it in C#. It would be nice to really convert it into Python in order to extract the features, volume features, such number of announcements, number of withdrawals, and some AS path features, such as AS path length, number of hops, then label refinement. As I mentioned, the first approach was to take everything with a Windows anomaly, which is really not realistic. So recently we have done k-means and isolation forest. We used algorithms in order to do label refinement. To extract from that window, when the anomaly was reported, points that are regular. It could work better. And then we do the, of course, data partition. And I said in our case, 60/40 was a good partition. And then we have to do data processing. We have to do feature selection. We do dimension reduction, of course, normalization. And then at the end, we do various machine learning algorithms. Many of these algorithms are publicly available and the packages are ready. So we use skitlearn, LGBN, PyTorch in order to select the parameters. We select the best parameters using k-fold validation. We use a 10-fold validation. And for that, we use a supercomputer because that's the most time-consuming task. So we are fortunate to have a supercomputer at some Fraser University, and we get the time and the memory. And so the validation is done using a supercomputer. I think we call it CIDR. And then we create a model, and then we do classification. And as I mentioned in our case, classification is the point anomalous or regular. Okay? This is a time series split for the 10-fold cross-validation, even though it was advised that for large data set, you should not do that. But for the sake of completeness, we actually do that. And we do this specific approach for time series split. And so we generate training and validation purposes. We do sets. We do that in order to select the best parameters. Performance, as usual. Training time is of interest for this application. Accuracy, F-score, precision, sensitivity. We also look at the entire confusion matrix because for some applications, true positives, false positives, true negatives, false negatives have meanings, right? You don't want too many alarms to go on, right, with false positives, but in some cases, you want the alarms to go on because it's a very sensitive power plant or control system. So we also look at these parameters, elements of the confusion matrix. Performance evaluation. This is the best performance for Pakistan power outage, right? We are using convolutional neural network. And as I mentioned, no refinement. Everything with the window is anomaly. Refinement using k-means. Refinement use isolation forest. 2 collection sites, ripe and routers. Training time, you can see 50 or approximately 50 seconds. What's color is the best performance. We look at accuracy. F-score is not very good. Precision is not very good, and sensitivity is not very good. But this is this is how these algorithms perform with this specific data set. Okay, so this is confusion matrix, true positives, FP, true negatives, false negatives for that for the very same data set. Okay? We also applied other algorithms, right? So a long short-term memory with 4 hidden layers. If there was no refinement, 4 hidden layers did the best. Training time is a little bit better, right? Just to give you a feel, what are the percentages we talk about. If we apply k-means to extract the regular points from the window of anomalies, LSTM2 worked best. That's the model with 2 hidden layers. Then with isolation forest, GRU did well with 3 hidden layers, and LSTM did well with 4 hidden layers. So what's read here are the best performances. The shorter training time, the best accuracy, F-score, precision, and sensitivity. And this is a confusion matrix, right? This is a Pakistan, oh, sorry for a second. Okay. So this is some other algorithms. As I mentioned, we also experimented with bidirectional LSTM, bidirectional GRU. So my students spend a lot of time, and I spend a lot of time looking at this, right? And so this is the confusion matrix for, I'm sorry, this is a light GBM. So it's a variety of learning algorithms. And something to notice, look at the time for light GBM. For the training time, we are talking order of magnitude faster. And that's why light GBM is one of the GBDT algorithms. It's preferred in this case when you want to react very fast if there is onset of anomaly. VannaCrypt for convolutional neural networks, right? We departed from k-means because it turns out that k-means doesn't do, or at least it does equally well as isolation forest. Isolation forest did a little bit better for what we call labor requirement, and so training time for CNN, right? And this is a confusion matrix. But just to give you a feel, now we're talking about accuracy of 58%, F-score 65%, precision 52%, sensitivity 87%. Okay. Other models, LSTM, GRU, with different number of hidden layers. So these are all just to give you a feel about what are the numbers we talk about. Right? And recently we also record the entire confusion matrix because it's very important for some applications. And so this is a BLS, broad learning system, radial basis function improvement. This is a cascades of features, right? And so you can see that the algorithm is very fast and it has decent performance. And this is about BLS for VannaCrypt. And I usually post my slides on the web so you can actually look at this data. One generic comment is BLS is very fast compared to the other algorithms, and it has comparable performance, okay? And so this is a variable features BLS, this is our contribution, and in some cases, when you select features, the algorithm is going to do well. Of course, it's going to be a little bit slower because you have to take a step in order to select features. So this is variable features BLS, right? You can see comparable performance. Training time is a little bit larger because you need that step to select the features. So this is variable feature BLS, right? Performance in terms of performance parameters and a confusion matrix on the bottom, okay? This is variables feature BLS with cascades. So that's every time I say variable feature, that means we are selecting the features, right? And so training time is still reasonable, right? But of course, a little bit slower. And this is the performance that we can achieve. For VannaCrypt and XGBoost was very fast, right? And so this is XGBoost. BLS and GBDT algorithms came approximately at the same time. And so now 3 or 4 years down the road, we can actually compare them. So GBDT algorithms did very well. Light GBM, you can see the training time in seconds. That's why it's called light. It has all these optimization approaches inside, and you can see quite a good performance in terms of performance indicators. And this is a card boost because some of features are categorical features. Vestrock and ransomware, this is a convolutional neural network, right? This is really for historical reasons. I'm just giving all the information. You don't have to look at this data or remember it. It's just the feel about what are the performance indicators, what is the training time, what does the refinement do? For example, in this case, k-means did better with the refinement, right? Isolation, Boris also did well in terms of time. It didn't do the best in terms of performance. So one has to compare. Right? And so this is bidirectional GRU, BLS, original, right? And variable features BLS. And we also did incremental version. Incremental takes a little bit more time, right? But it does a better performance. So I'm going to skip all this. I'm going to post it on the web, and I want to do the summary. First, we evaluated recurrent neural networks. We used bidirectional GRU, and it turns out for our data, in our experiments, 4 layers, BGRU with 4 layers achieved the best performance in terms of accuracy, F-score, precision, with refinement, and sensitivity without refinement. It had a comparable training time. Bidirectional version offered better performance, and it does have a longer training time because it has additional layers. Broad learning system, shorter training time than RNN, but somewhat inferior performance, 10 to 20%. Variable features and variable features with cascades, that's a modification to BLS, where you have a pre-selection of features. It had a better performance for specific data set that I didn't mention today. You always have to keep in mind that these algorithms perform differently for different data sets. GBDT, comparable performance to BLS, but it has shorter training time. And large EBM was the best. That's why it's called light. Labor refinement, in case of bidirectional RNN, cases with best performance, the isolation forest helped improve classification performance because it was able to identify regular points within a window of reported anomaly. So in conclusion, what I covered was various algorithms, LSTM and GRU as deep recurrent neural networks with variable number of hidden layers. So the little index 4, 2, 3, actually it's a number of hidden layers. We also visited BLS models with and without incremental learning, flavors with radial basis function. Also, we looked at cascades of map features and enhancement nodes in order to add the depth. And we also integrated extra trees for feature selection. And that was this contribution that I mentioned from my PhD student. We call it variable features BLS and variable cascade with features BLS. And we spent some time looking at GBDT, and we were very happy with that performance. Originally, we got interested in BLS because it comes from my community, and I know the Philip Chen, who actually was the originator of the algorithm, so we were curious. Later on, we moved into GBDT and found that these algorithms also do well. In terms of BLS and sort of novelty, offers comparable performance to deep learning, LSTM, RNN, and bidirectional RNN, and GRU models. Variable features algorithms employed variable number of features and groups of map features, and it had integrated this feature selection algorithm in the process. Advantages: ability to derive generalized models by using various subsets of input data to generate map of features. It does better than RNN and bidirectional RNN, and in most cases, other BLS models. It offers high accuracy and F-score. Okay? GBDT in general, better accuracy and F-score than BLS, but of course, the training time is going to be affected with the choices, number of iterations, learning rate, maximum depth, number of leaves in the decision tree. And as I mentioned several times, live GAPM had the shortest training time. I usually put references just to give credit where the sources come from. As I mentioned, RIPE and route use is publicly available. This is another data set that we experimented with. I didn't really mention anything about it today. It's very much used for image processing. And they had test bed for images, but you also had some communication data. More recently, we were also looking at test beds from Canadian sites, but this is from test bed. This is not from real networks. And the pretty graph of the internet showing you that it's a scale-free graph comes from Center for Applied Internet Data Analysis, and they had a very nice project called Walrus Project. So to show you the topology, I use the graph. Many tools, Python, Pandas, PyTorch, and sometimes it's really dangerous to have these tools because people just do trial and error. It's very important to understand what are the algorithms in there what are the features that I input? This is our own tool. We clean data, ready for analysis, report it to IEEE data port. I don't know if it's publicly available, but maybe for some fee, it's available, but it's clean, it's ready for the algorithms to be used. And we put both, right? So from write and from route views for the ones, for the Slama, Code, Red One, and Inda. I think we have to do it for route views also. Broad learning system, Philip Chen and his group actually put it online, so you don't have to code it. It's available from this side. 1 minute more. For intrusion detection, there are many papers. I listed here something that's readable. We talk about communication letters. We talk about survey tutorials, communication survey tutorials, something that's readable. Also, this report from RAND Corporation is also interesting. And so this is for general public, just to tell you that people have talked about intrusion detection. Most seminar work that we use in deep learning, of course, Hinton and his group, right? And so we also use the Goodfellow and Bengio and Kurvi's deep learning book, and some papers from transaction neural networks on LSTM. BLS and GBTT, these are two journal papers that I mentioned. Later on, I think recently there are more. Many people are evaluating BLS, but these are the two papers that actually introduce BLS in journal publications. IEEE transaction neural networks and learning systems in both cases. You can see 2018 and 19. And then these are three bottom references for GBDT algorithms: XGBoost, LightGBM, and CutBoost. And we also have our own publications. Everything is open and publicly available from our website. Journal publication, we have book chapters. These are a little bit older results. The first chapter talks about data. The second chapter talks about algorithms that we use at that time until 2017, because it takes time to prepare the book. And we do have quite a few conference publications. We didn't visit those places. We visit them virtually. The same way as today, I'm actually visiting Poland, even though I'm in Czech Republic. But everything is available and PDFs are open. You don't need a password or anything like that. So I just want to leave you with this view of our internet to tell you how interesting engineering endeavor it is, and the source of information for a variety of studies and projects in terms of traffic, in terms of topology, in terms of applying machine learning algorithms in order to improve internet performance and our daily lives. So thank you very much, and I'm sorry for running over time.
Thank you very much, Professor Trajkovic, for the fantastic lecture.
Thanks.
And I encourage you, all of you guys from audience, to ask some questions. Don't have too many occasions to ask such questions to such person like Professor Trajkovic. And there is a question: could you reject false positive, false negative results in some way? Can you add additional information like additional sensors in some cases that will be able to filter this? Do you think that it is possible in those applications?
That's very interesting. We actually discuss this kind of the confusion matrix with people from computing science who are very interested in these false positive and false negative. So we didn't work on it, but yes, it's a serious concern, especially for certain applications where you do not want alarms to go on too many times when you have false positives, but in some cases false negatives also. So thank you for the comment. We didn't look into this, and it would be nice to address this, because for some applications it's really important. It's not only performance of algorithms, but the look at the confusion matrix. And so this is why I added this confusion matrix with all our results. And we have been collecting these more recently within the last 2 years, because we realized that it's important. But we didn't do it until now.
Thank you for this question, and thank you for the answer.
Thank you.
So, and do you see the increased number of BGP-related attacks after the outbreak of the war in Ukraine?
We did, well, our collection is not very recent. The last collection is from January 2021, and we didn't look recently. And I bet it would be very interesting because there is a lot of disruption in terms of infrastructure, and it's definitely reflected, and it would be a nice topic to address. Our latest collection that we look at is for ransomware I think it's from January 2021.
Okay, thank you very much.
I'm sure it's possible to see, because even a minor thing like a trafo station in 2005 that went down for 4 hours overnight was visible, and I can only imagine how visible it is based on the situation that's happening now.
Okay, and how to build representative data sets to train BGP anomalies detection systems?
Well, this is why we posted something on IEEE data port. I don't know if you know, but IEEE has this data port when people upload the data sets in support of their publications. And the main reason is to have reproducibility of the results, because I can give you all these numbers, but it would be nice if you have capability to prove them right or wrong. And that's why nowadays, within the last decade, in a scientific community, we are very much concerned about reproducibility. And in order for you to reproduce the results, you have to have a data. So we have posted our data we use on Dataport, and some people also post the code. That's one way to tell you, okay, this is what represents, for example, Slama, Code Red 1, and then NIMDA for the period of time that we agreed it is. Data, you would like to have something like a test bed, right? Something that you can compare the results. And one way is to put the data publicly available, because RIPE and routers have collection sites. They have a data, but you have to work in order to extract the data. And sometimes people make a mistake. Like we found that 10 years ago we made a mistake, so we had to recount everything. But it's a good point, especially if you want to be able to reproduce result and then move forward, because, right, that's important. And so this is why I provide all this information so that people can check what we do.
Okay, thank you very much. And I don't see more questions now. I hope that next time we will see in Poland or in Canada, but maybe in person.
I was much closer today than last year.
That's true. That's true. And the same time zone.
Much closer.
Yeah. And actually in Warsaw, we have also a district of Prague. So you're very close to us.
Okay. Yeah, I came for the conference. I came to Belgrade 4 weeks ago, but you probably realized from my car that I happened to get COVID.
I hope that next time we will invite you to in-person meeting and
that would be very nice.
Lecture.
Yes, thank you very much for inviting me. It has been a pleasure and an honor to give a talk. So enjoy the IEEE day. Thank you very much.
Thank you very much. Pleasure is ours. Well,
yes.
Thanks a lot.
Stay safe and healthy.
Yes, same for you. And
Thank
of
you.
course, encourage you to stay here, or I know if you.
I have some other functions to attend.
Okay.
Yeah.
Thank you very much.
I'll stay for a couple of minutes, and I'll be happy to answer any questions. You just send me email, and I'm going to put. I can put my email here if you want, to all panelists, to everybody.
Yes, please. And if any of people in audience, if you have any questions to Professor Trajkovic, just please ask here in the panel.
Okay, so this is my email. I think I send it to panelists. I think that's the only thing I can do. And let me just put a website. And then I usually reply to email. I might be a little bit delayed because I am traveling, but I should get back to normal. So this is my website. And if you browse through publications on the left-hand side, you can find all the talks and everything else.
Thank you very much. Now, I'm sorry, but we will switch to Polish, because we have our winners and prizes for our contest in Poland, and we would like to read, all winners in this contest.
I'll listen for a while. Thank you very much.
Thank you very much.